In the next chapter, we're going to be reviewing stuff that you did in both Algebra 1 and Advanced Algebra, and also adding some new stuff onto it, because the next chapter we're going to deal with is about functions. A function basically is a rule that assigns each element of one set to a unique element of another set. The single most important word in that definition is unique. On the previous page, there was a picture that showed like a little machine where you had one thing feeding into it and another thing coming out of it. And the whole idea of a function is each thing that you put in, there's just one thing that comes out. Each input has exactly one output. You never have more than one answer when you have a function. Another way to say that is that when you have a function, each element of the domain is paired with exactly one element of the range. You actually did some problems back in trig class that involved this, and the whole idea was that every x had to go with just one y. That's how I can tell, looking at a problem like the third one on here, that it is not a function, because the number 2 is paired with both 1 and with 13. We've got one x that's paired with two different y's, so that one is not a function. Both of the others are, because all of the x's are different. It's okay on the second one that the y's repeat. What can't happen is for the x's to repeat. For a function, all the x's have to be different. You guys know that most of the time functions are defined using formulas. Most of the time we use a notation that looks like f of x equals something, like here f of x equals 2x plus 1. And you've done lots of problems before where it would give you a formula and say something like find f of 3. Well, if I found f of 3, the answer would be 7 because I would have to take 2 times 3 plus 1. In addition to a formula that says f of x, you can also define a function just with an equation. To do that, you have to be able to solve the equation for one variable in terms of the other. Typically, what we need to make it say is y equals something that's got x in it. And you need to make sure that when you solve it, there's only one possible answer. The top problem here, I could easily make say y equals 7 minus 3x. No matter what I plug in, there's just one possible answer, and that's why that is a function. On the other hand, the bottom one, if I tried to solve it, it would be y squared equals 7 minus 3x. I'd have to take the square root, and when you do a square root, you can get a positive or a negative answer. Because you've got two possibilities, that's why that one isn't a function. Here's two new terms that you probably haven't encountered before. The terms dependent and independent variable, and I'm actually going to mention those in the opposite order of what it says here. What we usually call x, the variable that you can plug in to get answers, we call that the independent variable. That's because you could plug in any number you want to, typically for x in a function. On the other hand, the answer, the variable that you solve for, which is usually y, that's called the dependent variable. The idea is that what y is depends on what number you plug in for x. So from your point of view, basically x is the independent variable, y is the dependent variable. There are a lot of other ways that you can define functions as well. Back when you guys were in Algebra 1, you probably saw some pictures like this that we call mappings. It's really no different than giving you a list of points, and the arrows are just showing what x is paired with what y. It really almost makes more sense when you have actual numbers with it. On the left, basically this is telling you we have the points 10, 15, 20, 45, 30, 25, and 40, 35. Again, the x's are on the left, the y's are on the right, and the arrows are just showing you what's paired with what. Since all the x's are different on that one, it is a function. On the other hand, on the right, I'd have the point 220 and also the point 240. There the x's repeat, and that's why that one is not a function. Another way that we can show functions is with graphs. And a kind of question you will be asked to answer is look at a graph and tell whether or not it's a function. The easy way to do that is using what's called the vertical line test. The idea is if a vertical line, a line that goes up and down, ever touches a graph more than once, it is not a function. So in this case, the graph down at the bottom is not going to be a function because you can see that the y-axis touches that in 3 different places. Up at the top, at the origin, and then down at the bottom. That's basically saying that when x is 0, there's 3 different points that are on this graph. And again, if x ever repeats, that tells you it's not a function. So anytime a vertical line would touch a graph more than once, it's not a function. On the other 3, any vertical line you ever drew would just touch the graph in one place. That's why the top 2 are functions. A couple of terms I already mentioned and I'm going to go into more detail on today are domain and range. The domain, it tells you here, is the values that make sense to put in for the independent variable. Remember, independent variable was x. So basically we're looking at all the x's that it would make sense to plug into a problem. Many, many times the domain is going to end up being all real numbers, or your book would write that as negative infinity to infinity. Anything you could plug in will work. And this basically means you have a rule that's defined for everything and everything actually makes sense. If you can't find some reason otherwise, probably the domain will be negative infinity to infinity. There are 3 things that can screw that up though. 2 of them have to do with algebra. One of those is that you can't ever divide by 0, which basically means you can't have 0 on the bottom of a fraction. And the other one is that if we're dealing with real numbers, which we always are with functions, you can't take the square root of a negative number. And so when you're trying to figure out what the domain is, what you want to do is look for those 2 possibilities and basically ask yourself, what would screw this up? We'll look at some examples of those in just a minute. But the other thing that can make a domain that's not just everything, not just negative infinity to infinity, sometimes is just the nature of the problem itself. For instance, you might have a problem that deals with money, and the kinds of numbers you're allowed to use are only whole number dollar amounts. When you compute taxes, for instance, these days, that's what you always do is round your money to the whole dollar amount. You can't put in cents. So, just that nature of the problem might force you to round things. You might also have something where maybe it's a geometric measurement and you know that means it has to be a positive number because you can't have like a negative distance. So if the problem has anything special about it, it might limit what the possible answers are. These are 3 examples of finding domain that are straight out of the examples in your book, and when you do problems, you'll be doing some pretty similar things. So we're going to take a look at these one at a time and figure out what would be the domain of each of these things. And we'll start off with this one that says f of x equals the square root of x plus 3. You actually had some questions kind of like this last year in trig class where you were asked to find the domain of some functions there. And you've got to think, when is this defined and when is it undefined? The important thing here is that when you're taking a square root, what's underneath the square root has to be positive, or more to the point, it can't be negative. And since what's under the root can't be negative, I know for a fact that x plus 3 has to be greater than or equal to 0. So that means x has to be greater than or equal to negative 3. I could pick any number bigger than negative 3, plug it in, and I'll get an answer. But if I try to put like negative 4 or negative 5, I'm going to be taking the square root of a negative number, and I cannot do that. The book would write this using interval notation, which is why we did that in the last chapter. They would say the domain is everything from negative 3 to infinity, including negative 3, because it's okay to take the square root of 0, and then going on forever. Here's the second example. G of x equals the square root of x over x minus 5. So in this problem, there's two things going on. One of them is the square root, which we would do pretty much the same way as we did the last square root. And the other one is the fraction. The big thing about a fraction is, remember, you can't have 0 on the bottom. So you need to figure out what would make 0 on the bottom of this fraction. The way you would get 0 is if you tried to plug in 5, because 5 minus 5 is 0. So I know right off that x can't equal 5. And also, because of that square root on top, x has got to be greater than or equal to 0. And again, the book would write it in interval notation. They'd say everything from 0 to 5, not including 5, and then everything from 5 to infinity, not including 5. So again, bracket 0, 5 parentheses, and parentheses 5 to infinity. The third example looks more complicated, but really, if anything, it's almost easier. It says a of s equals the square root of 3 over 4 s squared. And it also goes on to say where a of s is the area of a triangle with a side of length s. Now, the first thing we would do is check the algebra part of this. And while there is a square root here, there's no variable under the square root, so that's not going to affect anything in our answer. There's also no variable on the bottom of a fraction. So just from a pure algebra point of view, there's nothing that's going to go wrong here. You could plug in any number and square it and take it times square root of 3 over 4, and you'd get some answer. But there is something important with the second half of that, the fact that we're dealing with areas and lengths. The key thing is that geometric measurements have to be positive. You can't have like a side of a triangle that has a negative measure. And that's how I know that the domain here has to go from 0 to infinity. It can't be negative. And even though the problem technically would be defined for all real numbers, we can't plug in any of the negatives because they don't make sense for the answer. So the domain is 0 to infinity, not including 0. So domain, again, is all the x's, and we find it by thinking when would it be undefined or when would it not make sense in the answer. The range, on the other hand, are the actual values that you get for answers. It's what y ends up being after you work things out. You'll have some questions as well where they ask you what would be the range of this function. And basically what you need to do is think if there are any values that you can't have for answers. What you usually want to do is ask yourself, could the answer be positive? Could it be negative? Could it be 0? And sometimes if it's a more complicated function, you could even ask, could it be a fraction? Could it be a whole number? What all could possibly come out of the problem that you're looking at? I'm going to look at two different examples of finding the range of something. And again, these are basically straight out of examples in your book. The first one would ask you, what's the range of y equals the absolute value of 3x minus 7? Now in this problem, actually the 3x minus 7 doesn't really affect anything at all. What does matter is that it's absolute value. And you need to kind of ask yourself, so what happens when you take the absolute value of something? Well, the important thing is absolute value never is negative. If you take the absolute value of a positive number, you get a positive answer. If you take the absolute value of a negative number, you get a positive answer. And if you take the absolute value of 0, you get 0. So the answers we get would be everything from 0 on up. Y could be greater than or equal to 0. And that's why I end up getting a closed interval starting at 0 and going on forever, 0 to infinity. That's my range. So here's the other problem that we're going to take a look at, where we have y equals 1 over x. And you want to think, what would the range of this be? What sort of answers come out of this problem? And again, you want to kind of think through for a minute and think, could I get positive numbers for answers? Well, yeah, if you plug in a positive number, 1 over that number is going to be positive. Could I get negative numbers for answers? Yeah, 1 over a negative number is going to be negative, so you can get both of those. You could also get big numbers, you can get fractions, because the way you do that is you put in the opposite of that and do the reciprocal. There is, however, one thing you cannot get as an answer, and that's 0, because there's nothing you can do the reciprocal of to get 0. You could actually prove that by literally trying to plug in 0 and see what you get, and if you tried that, you would end up with something that doesn't make any sense, that 0 equals 1. So what happens on this one is the range ends up being all real numbers except 0. You go from negative infinity to 0, skip over 0, and then go from 0 to infinity. So everything but 0 is going to be the answer. Tomorrow we're going to take a look at a few more things involving functions, but for today you want to remember how you can find the domain and the range, and you want to be able to look at the different ways functions can be represented and tell whether or not something is a function. Again, the key thing is all the x's are different. So that's where we'll leave things for today. We'll pick it up and look at some other stuff tomorrow.